Okay, I think we are ready. So, well, it's actually my pleasure to introduce the speaker today within the Plan Visita. His name is Dr. Alexandros El Sachat. He comes from the University of, or for the National Research Center of Demokritos in Greece. He obtained actually his PhD at the Autonomous University of Barcelona, so he knows our country pretty well. He's an expert on thermal and thermoelectric characterization of different type of nanostructure materials and 2D materials. He also did a postdoc at the Institute actually of Barcelona, at the ICN2. And he obtained also Marie Curie individual fellowship, a very prestigious one, for carrying out also measurements and characterization of 2D and other nanostructure materials. Later on in 2023, he obtained an ERC, a starting grant, also very prestigious, to explore transport phenomena in 2D materials and nanoconstrictions for developing energy-efficient nanoelectronics. Alexandros, it's a pleasure again to have you here, and we are all looking forward to listening to your presentation. Thank you very much. Sorry, just one more thing I forgot. So there is a list of assistants for those students that need a certificate afterwards, and you can sign it after the talk. Right, sorry.
Thank you very much, Miguel. Do you hear me, everybody? Yes. Okay. Thank you very much for inviting me here. It's really my pleasure to be here. It's a very nice opportunity to meet you all. Thank you also to the director for a very nice overview of your institute. It's really amazing, and I see that it's growing. So I'm coming from the National Center of Scientific Research, Demokritos. Okay, let me see. That is okay. That is here. Okay, and the idea for this talk, it was first to show you an overview of the research activity of my group, which was created last year, thanks to the ERC funding. And then I would like to show you some specific results relevant to these activities, which I think you will find interesting. This is my group. It's called Nanoscale Transport Phenomena Group. So we are working, we dedicate our research in understanding energy transport phenomena in low-dimensional materials and devices, and specifically we are working with thermal and thermoelectric transport at the nanoscale. We are a small team, have one PhD student, 3 postdocs, and 1 project manager, who is very necessary to overcome all the bureaucracy issues and the paperwork that for sure you have here as well, and you understand very well. Okay, this is the outline of my talk. First, I would like to show you the main challenges in the thermal transport community, in my opinion. Then I will show you the strategies that we are following in order to overcome these challenges. And then I would like to show you some specific results. We will see how we can tune the thermal conductivity of low-dimensional materials, the engineering part of the materials. We will see different material systems, silicon membranes, 2D materials, and phononic crystals. Then I would like to dedicate some time in order to show you how we can probe anisotropic thermal transport in layer materials, and how we can really understand ballistic and diffusive thermal transport at the nanoscale. And then I would like to show you some new results that we have related with thermoelectric devices based on 2D materials. And then I will end up with the conclusions. So the main challenges. Okay, so one of the main, let's say, scientific challenges that we have is to really to understand energy transport and conversion at the nanoscale, and specifically in 2-dimensional semiconductors, which is expected to be the core material platform for the next generation electronics, in my opinion. Now, the difficulty to probe anisotropic energy transport across dissimilar interfaces, nano-heterostructures, and electrical contacts actually have led to two main technology issues that we have today, and you are familiar on. One is the poor thermal management that we have in nanoelectronics, where the extreme heat that is generated at the local hotspot of these devices results in increased power consumption, overheating, and in many cases, device failure. And the second thing is the low-efficiency thermoelectric conversion systems that we have nowadays that produce power less than 1 milliwatt and have efficiency of less than 10%, that actually limits their practical application in low-power electronics. So, if you think about the 3D scaling and the future 3D stacked chips that we are aiming to develop, where we actually combine computing and data storage, where actually we have memories and transistors on top of each other, and this is expected that will become reality in the next few years. We see that here the problem is even more important, that we have heat flux densities on the order of 50 kilowatt per centimeter square, and this exponentially increases as this high density integration is moving forward. So it is very important to have this directional thermal management and cooling in our chips. It is important to be able to control the heat flux in specific directions. So the question here is, can we control the Phonon and energy dissipation at the nanoscale? And this is exactly what we are doing in my group. So we start from from the beginning, when all this research started, and we were working with membrane-based structures. And what we would like to do is to adapt 3 different methodologies in order to engineering the Phonon dissipation relation, and in general the thermal properties of this material. So in membrane-based structures, we are following the methodology of, we are using the confinement, we are using the external stress, and we are using also the nanopatterning. So with all these 3 methods, actually we can modify the Phonon dissipation relation in our materials, we can create Phonon band gaps, and we can really decrease the thermal conductivity. And I will show you later on how we can also control the heat flux in these materials by creating this kind of phononic crystals. The same thing we are doing also with 2D materials, and this is something that we did recently. So how we engineer the 2D materials. So again, we are using, so what I was telling you, how we engineer these 2D materials. So we are using nanopatterning to create nanoporous materials in order to create these heat guiding and insulating channels on top of the 2D materials. I will show you later on how we characterize these materials. We are using phononic crystals, disordered, and gradient structures in order to really guide the heat flow in specific directions. And if we go to smaller scales, we are working with super lattices and heterostructures. So we are growing with different techniques, epitaxial techniques, molecular beam epitaxy, and atomic layer deposition, this kind of atomic layers on top of each other in order to control, in this case, the cross-plane heat dissipation. And of course, always a good method is the twisting. I don't have a lot of results to show you about this, but it's also something interesting, because by twisting the 2D materials, actually we create this lattice mismatch between the atomic layers, and it's something interesting and to be investigated. So, okay, and if we think about the phonon spectrum, okay, so we are interested to see, phonons, the high frequency phonons actually. We want to adapt, to employ these phonon engineering approaches in order to see if we can control the heat flow, and potentially we can increase the thermoelectric power generation, and we want to have access to the high frequency phonons, the phonons that they have high energy, and usually in low dimensional materials this happens for phonons above 1 terahertz. And this is the spectrum of phonons that we would like to control. And in order to do this, we need to work with advanced thermal characterization techniques, and this is what we are developing in my lab. So first we are working with the frequency domain thermoreflectance, an interesting technique where you can probe interfacial thermal transport, you can measure the cross-plane thermal conductivity, and you can determine the thermal conductivity anisotropy, which is interesting, depending, in many cases, depending on the film thickness that you have. I will speak later on about this technique. Then we have, so the first thing is, the first thing is the frequency domain thermoreflectance, then is the scanning probe microscopy. Here, let's see if we have time. I would like to show you two different modes of this scanning probe microscopy, the scanning thermal microscopy and scanning thermal gate microscopy, where we can really probe thermal and thermoelectric transport in active devices, and we can see the temperature mapping in active devices. And then we have the 1 and 2 laser Raman thermometry, this that I used to use during my postdoc time in ICN2, and we still have collaboration, and we are still using this technique. Then, so we talk about the phonon engineering approaches that we would like to engineer the materials, the advanced characterization methods, and then we have, this is the final goal, what we would like to do is to create devices for on-chip cooling and power supply. We would like to create this kind of nanogenerators based on thermoelectric, based on TD materials. And here the main goal is the directional heat flow that we can create in this kind of devices, active and passive cooling of hotspots. This can be either passive cooling by using a high thermal conductive material, or by creating a nanogenerator and perform this, how we call it, thermoelectric cooling. And the idea here is to increase the thermoelectric efficiency of this device and produce high power. Okay, so let's go to the second part of my talk, which is let's see some specific results and how we are doing this. Starting from the first part, which is how we can tune the in-plane thermal conductivity in low-dimensional materials. So we did this. The first thing what I mentioned is the confinement. So here, what we do is we started from bulk silicon, and we went down to 8 nanometer thick silicon membranes. And in the second study, also we did this with molybdenum disulfide. We exfoliate layers from 1 layer until 70 layers, and we measure the thermal properties of this material. There's the in-plane thermal conductivity, and the idea here is that by decreasing the thickness of the membrane or the silicon membrane, actually you increase the phonon boundary scattering, so you can really decrease the thermal conductivity. So we measure this with the 2 laser Raman thermometry. I will not say a lot of details about this technique, which is very well established. 2 lasers, 1 laser to have the thermal excitation to create the thermally spatially dependent thermal field, and 1 is the temperature sensor. And by using this model, actually we can extract the thermal conductivity by measuring the absorbed power, the thickness of the membrane, and this factor which we get from the experimental data, which actually is this slope. So what we found here is by starting from bulk silicon, and when we decrease the thickness, we can have, we end up in a silicon membrane with 8 nanometer thickness, and we can reduce the thermal conductivity by more than a factor of 1. Sorry, 1 order of magnitude, sorry. So this means, by a factor of 10, yes. So this means that this is an efficient way to decrease the thickness in order to decrease the in-plane thermal conductivity. And this is happening because we increase the thickness, we increase the phonon boundary scattering, so the thermal conductivity is decreasing. On the other hand, we see that by increasing also the temperature, the phonon umklapp scattering processes Here you see that by increasing the temperature, actually we increase the phonon umklapp scattering processes. So we have more phonon scattering in our membranes, and again we see this trend of decreasing the thermal conductivity. But we can do this with more efficient way by creating phononic crystals in the silicon membranes, and actually we don't have to end up with a thickness of membrane of 8 nanometers. We found the same results and even better results by in a 250 nanometer thick silicon membranes by creating this kind of phononic crystals on top of the silicon membranes. So we were able to again reach very low thermal conductivity values. Okay. The other interesting thing is that we did also this in 2D materials and it's working the same. And you see here how the nanopatterning on top of the molybdenum disulfide flakes decreases the in-plane thermal conductivity. From 32, the pristine MOS2 goes from 32 to 88 watt per meter Kelvin. But then, if we create some phononic crystals on the top, this thermal conductivity can be decreased by a factor of 10. But the most interesting on this study is that we can really control the heat flux in our suspended membranes. Here you see some specific patterns that we did on top of the molybdenum disulfide flakes. This insulating ring where we create two different areas called areas around the insulating ring, and in the middle is the hot area. Here you see the temperature profile. So I will not use probably this because this is a problem. Okay. And you see that we can create different areas with different temperature on top of the suspended material. Then you see in the bottom that we can create some specific patterns again in our membrane, and we can really, and the heat flux and the heat flow that we created here in the hotspot actually follows the patterns of the FIV patterns that we created. So this is a nice demonstration to show that nanopatterning can actually guide the heat flow in pre-specified directions, and this is something interesting if this this result is working also in devices where we have hotspots. So the idea is that if we can implement, we can integrate these molybdenum disulfide flakes on devices and see a similar trend. Of course, there will be more difficult because we have the effect of the substrate, but this is the first demonstration that nanopatterning can be used for this purpose. Okay, let's go to the second part, is how we can measure the anisotropic thermal transport in 2D materials. Here we used two complementary thermal characterization techniques, the two-laser thermometry and the frequency domain thermoreflectance. With the first technique, we measure the in-plane thermal conductivity of these flakes, and the second technique, which is here, which is the right part of the image, we measure the cross-plane thermal conductivity. And here you see by performing these measurements, we can extract the thermal anisotropy. So we can say how much heat flux propagates in plane and cross plane in our membranes, in our 2D materials. And one interesting thing here is that we have the in-plane thermal conductivity that is changing with the temperature. So we saw that actually the membrane thickness doesn't matter anymore if we go at very high temperatures, since the phonon battery scattering becomes dominant. Now, another way that we recently developed in my lab is to measure the thermal anisotropy in these materials by creating a unified thermal characterization system. So we don't have to change, we don't have to take the sample and measure it in another setup. So this is happening in one setup. So this is a unified setup that consists of, I will not use the pointer, I'm scared. so it's, we are using a line-shaped heater, okay? Instead of having a Gaussian spot, we have a line-shaped heater. And then we have a Gaussian spot, which is next to the line-shaped heater, where we can measure the temperature. So this line-shaped heater, actually, we modulate this pump laser. This is the pump laser that creates the heat flux in our 2D material. And with the green laser, actually, we probe the temperature. So the left part of this image that you see is how we measure the in-plane thermal conductivity in our material. And the key advantage of here is that we don't have any heat that propagates along the direction parallel to the line-shaped heat source. So this is something very important because somehow we boost the heat flux to go to the in-plane direction. So we create a temperature gradient in the in-plane. So then we can go with the laser with a Gaussian beam and probe the temperature. And then you see on the right part of the image, you see a conventional frequency domain thermoreflectance where we can measure, as usual, the cross-plane thermal conductivity. So actually, by having this setup, we can know exactly the thermal anisotropy, performing this measurement, the thermal anisotropy of the materials. And this is something interesting if we really want to see the thermal transport characteristics of the materials that we would like to integrate in our devices. For example, in transistors. Okay, so I will not go to the details about the model. We lost also some time just to show you that this technique can be applied also for the 2D samples and also for 3D samples. And this finally we end up by starting from the heat diffusion equation. We end up in an expression where actually we have the second derivative of the phase lag that we measure with respect to the position of the modulation frequency, and where we can extract the thermal diffusivity of our material, which is the thermal diffusivity. And then from there, we can extract the in-plane thermal conductivity, since we know the heat capacity and the density of our material. So these are the experimental data, what we get, the phase lag as a function of the spatial offset, and there the slope of these linear fits actually give us the in-plane thermal conductivity. So we did this for the tungsten disulfide films, one of the first demonstrations, and we found a very strong dependence of the cross-plane thermal conductivity as a function of the thickness. We also calculate the accumulated thermal conductivity as a function of the mean free path. So actually this gives you which phonons propagate in our material. It tells you which phonons, the percentage of phonons that contribute in the thermal conductivity with a certain mean free path. And here you see in the other two graphs, here you see the in-plane and the cross-plane thermal conductivity as a function of the thickness and the temperature, from which we can extract directly the thermal anisotropy in our material. So you see that the thermal anisotropy can be tuned somehow depending on the temperature that we are using or the thickness, which is quite useful if we want to design a new device from the beginning. So we really need to know the thermal transport characteristic of our 2D semiconductors that we are using. Okay, so we saw how we tune the in-plane thermal conductivity. We saw how we can measure the thermal anisotropy, and let's see what about the cross-plane thermal conductivity. So for this, we are using superlattices. We are using layer stacking, either by exfoliation or by growing using epitaxial methods. So in this, and the question here is what materials, what are the proper materials in order to create these superlattices? So here we would like to take advantage of the Phonon interface scattering. So what we would like to do here is to create materials on top of each other and create several interfaces in order the phonons that propagate in the cross-plane direction to scatter more, so the heat flux, the cross-plane heat flux to be reduced. So this is the idea. So which are the materials to do this? So we need to select materials with large mismatch in the acoustic properties that have a very different Debye temperature ratio and large lattice mismatch. Okay, so this, so what we did is to create this kind of superlattices with molybdenum disulfide, molybdenum diselenide, sorry, and bismuth selenide. So these materials have very large lattice mismatch. So we created superlattices based on these materials, and then we created also layer stacks based on graphene monolayer and layer palladium diselenide. So why we did this? Because this is completely the extreme scenario where we don't have any lattice mismatch. So we wanted to see the two different extreme cases. So we grow these materials in an ultra high vacuum molecular beam reactor. So we can grow materials up to 8-inch diameter wafers. So this reactor consists of several EGAN evaporators and diffusion cells where we can load our materials. So we can grow these materials layer by layer. We have very good control of the thickness of these materials. And then the interesting thing is that we have also two separate chambers where we can do the in situ structural and chemical characterization of the material. So we can really know what kind of material we are grow, what kind of heterostructure, and all their properties. So these are some examples of what we grow. Bismuth selenide, molybdenum disulfide, and you see several layers, a bilayer of molybdenum disulfide and bismuth selenide of 1 nanometer grown directly on STO or on STO substrate. And we made these superlattices. So you see here the superlattices made of bismuth selenide, molybdenum disulfide, bismuth selenide, and so we create several interfaces on top of each other, and then we grow graphene and several layers of palladium diselenide. And if we measure this, we show that we have, and if you look better at this graph here, and you see this is the thermal resistance of the film that we measure, okay? And what we found is that in the ballistic thermal transport, we have ballistic thermal transport in graphene palladium diselenide heterostructures, since the fact that we don't have any lattice mismatch interfaces, and we have a large phonon spectra of the graphene that actually give us this phonon propagation in the cross-plane direction as well. However, in the superlattices, we have diffusive thermal transport due to the fact that we create this kind of interface phonon scattering, the interfaces, and we have phonon scattering between the interface, and this is the result. I will try to, it's here. So these are the superlattices that give us, okay, hope it didn't stack, okay, give us the a high thermal resistance. So, so this is a way somehow to control the heat propagation in the cross-plane directions, because these superlattices can be used as an active material in devices. So if we manage to keep the long-range crystallinity of these materials, we can still have heat propagation in plane, but we kill the cross-plane. Okay, so it was the idea of this work. Okay, another way to study also ballistic and diffusive thermal transport is by using scanning thermal microscopy. Many of you, I think, you are familiar with this technique. Just a few things. So we are using thermoresistive probes. In this case, in this work, we used some probes specialized in IBM, where they have some silicon probes that are aged, and they create a very nice deep apex at the end. So the idea with this technique is that you can do a temperature mapping in the device, in an active device. So these sensors can be used as a thermometer, but also can be used as a heater. So they can do two things. So in this case, what we did, what we wanted to see is how the heat dissipation is changing by increasing the graphene lateral size. So we want to see any crossover from the ballistic to diffusive thermal transport in these graphene flakes. And how we did this, we grow this with CVD, and then we transfer this in silicon dioxide, so we create suspending graphene with different diameters. So we want to see which is the impact of the ballistic resistance or the thermal conductance measurements. So in this case, we use the heater, we use our probe, our tip, as a heat source. Okay. So, and we perform some thermal conductance measurements. So we need to take into account several things, but in general, these measurements actually give us the thermal conductance of the tip sample thermal contact. Okay, and you see here that we have this is the signal that we get when the tip is out of contact, and after the thermal conductance that we get when the tip is in contact. And this is the model where we can extract the thermal resistance of the graphene itself. And here you see that this thermal resistance first is decreasing as a function of the radius, and then you see this crossover, and this again the thermal resistance is increasing. So here we have when we have these graphene flakes with radius much smaller than the phonon mean-free path graphene, we have increased heat dissipation due to the fact that we have increased population of the low-frequency acoustic phonons. So here we are in this regime. And then you see when we are passing to the diffusive thermal transport, when the radius of our graphene disk are much larger than the phonon mean-free path in graphene. So there, what is happening is that we have phonon-phonon scattering. So these are the resistive scattering processes in our lattice. And then this scattering actually increases the thermal resistance that we measure in graphene. And this is the thermal map that we get, from this measurement. This is the STHM mapping, so we can see difference, the quality of the graphene and many other stuff. Okay, let's go to the last part, the last example that I would like to show you, how we can do thermoelectric measurements in using scanning thermal microscopy. So let me first introduce you the way that we perform the thermoelectric measurements. Usually we have this kind of prefabricated chips that have several pads. Here we have two different heaters. These are the big lines, are the two different heaters that we have. In the center are the thermometers. And usually we exfoliate flakes, just exfoliate flakes on the top of the two electrodes, and we perform these thermoelectric measurements. And we measure the Seebeck coefficient using these two pads. So one thing that we found that is interesting is that the nanopatterning that I showed you before also give us very good results in the Seebeck measurements. So we wanted to understand this because it's not something straightforward. Because we know that the thermal conductivity, I showed you before, that the nanopatterning, we can decrease the thermal conductivity of our material, we can even guide the heat flow. But what about the Seebeck? So why the Seebeck to be increased when we create patterns in our material, when we create nanoporous membranes? Why the Seebeck coefficient to be much higher? So we wanted to understand this. And to do this, we employed a scanning thermal gate microscopy technique, which is a different version of the scanning probe microscopy, where we have a three-terminal device, where actually we are using the tip as a hotspot, and we scan the tip over the sample. There we connect, I have to use it, sorry, let's see. So here we connect with the two electrode devices, here we measure the thermovoltage, and we have the tip that is on the top of our flakes. And as the tip scans the sample, the tip modifies the potential voltage drop across the two terminals that we have, And we can have a thermovoltage mapping. So here you see one example of thermovoltage map in monolayer and bilayer graphene. And from this thermovoltage map, we can extract the local Seebeck coefficient of the materials. So why this is important? Because when we do this patterning, we really want to see around the holes thermal and thermoelectric transport. We want to see what is happening around the holes in the boundaries. So we did again these devices. We made new devices. We create a systematic study to see how this nanopatterning, how to create these nanopatterns in order to have a conclusion about what I was telling you before. And we found something interesting. We found that the thermal, here you see a thermal map. Let me first explain you what we see here. You see a thermal map of our patterns that we create with the holes. Okay? So you see in this case the thermal conductance and the difference, the thermal contrast between our patterns and our substrate is very well defined, as you see. So you see a very different color inside the holes. However, in the thermovoltage, you see the thermovoltage spread around the holes of a few hundred of nanometers. So, okay, we found this, and this is not something straightforward to understand. And we say, okay, which is the reason of this? Why in the thermal is very well confined here, while with the thermal contrast it's very well aligned with what we were expecting, while in the thermovoltage we have this extended thermovoltage, we have this extending signal around the holes. Okay, and this is not only this. It's also accumulated the thermovoltage by creating more and more patterns. We accumulate the thermovoltage and we create areas of a completely different Seebeck coefficient, completely different thermovoltage. So this means, so as you see here, so by creating, we found the proper patterning in order to create completely different Seebeck coefficient left and right to the pattern that we create. So why this is important? Because actually we can get any material that maybe it's not even thermoelectric, and you create around the material thermovoltage out from nowhere. So you can create a thermoelectric response on the material, either to increase the thermoelectric response or made one material that is not very well thermoelectric to increase its thermoelectric properties. So this is a study that's ongoing. I don't want to say more about this, but this is also, we have some calculations to understand these thermovoltage profiles and the Seebeck measurements. And with this, I would like to go to the conclusions. So first, we saw that this large area cross-plane thermal insulation and the directional in-plane heat flow can be achieved by different methods. We saw the lattice mismatched van der Waals superlattices, the nanopatterned 2D materials, and this is hopefully useful in order to avoid the heat spreading into the substrate and the hotspot formation. We saw that the tungsten disulfide exhibit thickness temperature-dependent thermal anisotropy. I presented you a new technique that we can really probe the thermal anisotropy in these materials. We saw that it's possible to create large areas of the Seebeck coefficient modification by simple patternings with this scanning thermal gate microscopy technique that we can really probe thermoelectric transport. And as a general comment, conclusion is that the use of the combined optical and electrical thermal characterization methods is important to understand nanoscale thermal and thermoelectric transport phenomena. So with this, I would like to acknowledge all the people that work with me and continue to support me. Really, I'm grateful, and thank you very much for your attention.
Now the floor is open for questions.
I have a question, Alex. Thank you very much. It's super interesting talk, but I don't don't get, it's okay, I don't get the role of the phononic crystal in the heat guiding. Like, you don't have a gap, you don't have coherence.
Yes, I think I should say it a bit differently. Let's say nanoporous membranes, because of course the phononic crystal is not something that it's really necessary in our case. We don't really need to create the band gap in our material, but sometimes because we use these samples for also to study the, let's say, in the hypersonic range and measure, for example, with brillouin. I just call them phononic crystals, but you can call them like nanoporous membranes. Okay, and the fact here is that depending on the characteristics, for example, of the neck size or the diameter that we choose to pattern our materials, we get completely different results in terms of heat flux. So this has to be related with the characteristic length scale of the material that we have, has to be related with the electric in the Phonon free path that we have in the material. Doesn't mean that, for example, in a tin diselenite that we work, we use the specific pitch for our holes, for example. But, for example, if we go in a material that has a very higher thermal conductivity, we should consider this pitch might be different because it has to be related with the Phonon free path. And the Phonon free path is changing. So actually, if you think these holes as scattering centers, you will somehow conceptualize all this work.
Thank you so much. Really nice talk and results. I was wondering, would you mind going to slide number 24? There. So here, if I understood correctly, you have some ballistic cross-plane conductivity, right?
Yes. Okay, so here I didn't have time to explain it very well. Actually, I passed it a bit fast. The first graph is the interface thermal resistance that we measure. So, and this consists of two different components. The interface thermal resistance of the transducer that we are using with the film, and the interface thermal resistance between the film that we have with the substrate, R1 and R2 that I explained a bit before. So this is the R interface, okay? There, okay. And then we go to the R total. The R total actually is the R interface that we have here, plus the thermal resistance of the film itself. Okay, so then you see that this, when this R total is not changing, so by increasing the thickness, the thermal resistance is not changing. This means that inside the material we don't have any internal scattering. So the phonons propagate without any scatter.
Yeah, I mean, could it be also that you have very large boundary resistance and you still not actually, and what you're what you're measuring is only that?
No, but the thermal boundary resistance is this, exactly, is the first graph.
Exactly, so, but in order to be able,
but here is 10 and the other is like 80. So the thermal boundary resistance it's 8 times less than what I present in the second graph. So there is an effect of the boundary thermal resistance, but it's smaller.
Okay, because it's a bit surprising, don't you agree? I mean, that to see cross-plane ballistic transport.
Yes, because we are in the case of scenario not of the superlattices, but we are in the case of the palladium diselenite. So imagine here we have silicon carbide, and we grow this by CVD. We have excellent thermal coupling. The graphene, in the best case scenario, has to be grown in silicon carbide. This is the perfect way to grow graphene. Then, with this way, you have actually very, very small thermal resistance between the graphene and the silicon carbide. Actually, almost zero. And then we grow the palladium diselenite. The palladium selenide with graphene has zero thermal mismatch. So it's like you have a film. It's like, I mean, it's like have a film without any interface. This is what we get here. So this corresponds to the red data points. And this is, we don't see something to change the resistance. However, in the superlattices, it's very clear that it's changing.
Okay, thank you so much.
Do you have control of the stacking?
Sorry?
Do you have control of the stacking of the different layers in these examples?
Control of the stack, like to create an angle.
No, basically you have an AB stacking or you have a whatever stacking in these cases. Because I guess also the stacking will have a consequence in the heat flux in the cross plane, right? Or
Yes, so you mean if the orientation of the...
different layers are the same in all experiments, well, ideally.
No, are the same, yes. Yes.
And in the case, in the previous slide that you showed that the conductivity increases as a function of the thickness. In this case, you have only one material.
In the previous...
In the previous slide, when you have that the crossover heat flux increases as a function of the thickness of your system. I guess this one, for example, the right, the top left.
Here.
No, top left. Oh yeah, well,
Or
for
there.
example,
the crossplane, yes.
Exactly.
Yeah.
Because also for me, you have an idea why you have a better conduction when you increase the thickness. Because I will expect more scattering because the van der Waals interaction different for the different layers. Do you have an idea?
So one big difference is that here is exfoliated, single crystal.
Okay.
So we don't have any defects, we don't have nothing. So actually you see that the tungsten is starting from 0.01, something very small, and goes until 1. So it's by a factor of 10 until 200 nanometers, which is something expected. This is that we found.
And which kind of material is that?
This is tungsten disulfide.
Okay.
And the tungsten disulfide has larger thermal conductivity. The intrinsic thermal properties are much better than the others.
For example, this.
So the others, the bismuth selenide and the molybdenum disulfide has much lower thermal conductivity in general.
Okay.
So the variation with the thickness will be, it's expected to be smaller by increasing the thickness.
For example, thinking in another thing, but in regarding friction properties, you also notice that you have in some 2D material, you observe a decrease of the friction as you increase the number of layers, and is associated with some. You decrease the puckering effect and blah blah blah. But here, for me, it's a bit I will expect more scattering as you increase the number of layers, because you have to cross many boundaries in some way. Because for me, it's a bit counterintuitive. So I will expect that if you do a theoretical analysis.
So imagine that here, yes, I know how you think about it. Here, there are not interfaces. I mean, this is a way how you exfoliate. So when you exfoliate from the bulk directly, you get the material, a thick material, without any interface. So when we said, okay, it's 200 nanometers, there are not several interfaces.
Yeah, now I understand. Thank you so much.
Okay, but in the previous, it was, we grow layer by layer.
Okay.
So
now, now it's a bulk, we can say.
Okay,
thank you so much.
So thank you so much for the talk. I had a curiosity at the very beginning when you introduced the different strategies to tune thermal conductivity. In the slide where you introduced the nanopatterning, there was a graph where I think I saw that the decay with the temperature, depending with the pore size, I think it was different. It was at the very beginning.
The phase velocity that I mentioned. Here.
No, even before.
In the introduction.
In the introduction, there was I couldn't see the slide number.
Can you repeat what
it was? It was the decay with when you increase the temperature of the conductivity with respect to the pore size.
Ah. Okay, maybe
That one, yeah.
should be here.
Are those exponents the same? Because
So, okay.
I wonder if there's a difference. Why is that? If when you change the pore size.
Okay, good question. So here in semiconductors in general, the temperature dependence is following the trend 1/T with a factor of n. Okay. So in silicon there's a specific number that corresponds to this factor of n. The higher is the factor this actually give us the indicates that we have a stronger temperature dependence. Okay. This is the general. So here you see from the bulk we have something like goes to minus 1.31, right? And then we go to the 250 nanometer silicon membranes, and as we decrease the thickness, this factor is decreasing. Okay? And this is because we have two different mechanisms when we decrease in the thermal transport. The two different mechanisms are the phonon boundary scattering that is becoming more important as we decrease the thickness of the membrane, and then we have the phonon-phonon umklapp scattering processes. So these are the resistive processes that are responsible for this temperature dependence. So when we decrease the thickness, this phonon boundary scattering becomes dominant. So that the dependence with the temperature of the thermal conductivity is smaller. And this is why this factor is decreasing. So actually it's telling us that the temperature dependence is no more significant.
It's a compound effect between both mechanisms. Is it?
Yeah.
Okay.
Yes.
Thank you.
What do you expect from twisted layers? It's kind of, specific patterning, for example, as a result of the moire that you are giving up.
Having a twisted two layers and pattern the two.
No, what I mean is that you can understand somehow that the moire promotes some kind of already pattern layer, because you have a high strain and low strain areas.
Yeah, it's true, it's true. Yes.
What do you expect out of stacking of twisted layers?
Actually, there is a very nice work published, I think, in Nature a few 2 years ago or more, where they did this kind of what you were saying by exfoliating molybdenum disulfide, I think, atomic layers, and they were stacked in different angles, and they managed to get very high thermal insulation. So they managed to get high thermal resistance, and actually these values that we got are very close to these values, and the ones that we published. So yes, this is another way which is very interesting. It's already done.
More questions? I have one, actually. Now that you can engineer the thermal transport across these heterostructures, and you are exploiting quite a lot like different designs for thermoelectric phenomena in plane, have you considered that cross-plane low thermal conductivity for creating like efficient thermoelectrics?
Yes. This is so. In the beginning, when I was explaining the different methodologies that we were doing in my group, so the first it was this phonon engineering, and in this part, we are interested also to reduce the cross-plane thermal conductivity. So when we integrate these materials in the thermoelectric generators to have better efficiency. So this is what we are doing. Yes.
All right. So if there are no more questions, then let's thank the speaker again. Thank you, Alex.
Thank you.